circumference of a circle. And this is defined as that distance along the curved path of a circle, the perimeter. Okay, and it's the distance around the entire circle, okay, from one point on the circle all the way back to itself, around the circle in that way. And the circumference is calculated as d pi. So this is the most common sort of definition for this. Okay, but since the diameter is also represented of twice the radius, you can also have a second equation for the circumference of a circle where you replace d with 2r. And so that gives you a second equation, 2 pi r. So these are your two equations for the circumference of a circle. Now, the actual definition of pi is, like when you are defining pi, pi is simply the irrational number that represents the ratio of a circle's circumference to its diameter. And so that's part of where like pi is defined in terms of this circumference. Okay? So if you're being asked questions about just the basics of circumference, it will look something like this. Go ahead and answer that question really quickly. Like I said, this is the one that's intuitive as well as something that you've probably talked about in like 5th or 6th grade when you started dealing with geometry concepts. So your circumference is 14 pi. You can choose one of the two formulas, right? Either d pi or 2 pi r. Since the question asks you for the radius, let's use the formula that has a radius in it. So 2 pi r is equivalent to 14 pi. Isolate and solve for the r. We divide both sides by 2 pi. Pi's cancel. 2 goes into 14 7 times. And so there is your radius. Okay, the radius is a one-dimensional measurement. Circumference is a one-dimensional measurement for the circles. Now, there's also an arc length that you need to be able to find. Okay, so arc length differs from arc measure. Remember, arc measure represents a degree of rotation that coincides directly with the central angle on an arc. The arc length is the portion of that circle's circumference that's contained between the arc. Okay, so if you take your arc from A to B and you want to find that total length, like what the distance would be to travel from point A to B along that curve, that's the arc length. And arc length is given with this S with kind of a curly finish on the bottom. Okay, and arc length is some portion of a circle's circumference. Well, the portion is given as m over 360. And then it's just the circumference calculation. So just like what we saw up above, that calculation could either be, it might just give you that this is the circumference of the circle. If it has a central angle of whatever, what's the arc length? You could just use this formula exactly as it appears right here. But more than likely, you're either going to be given the radius or the diameter. And so you have two alternate versions of this. M over 360 times d pi if your problem involves a diameter, or m over 360 times 2 pi r if your problem involves a radius. And so it's going to be one of those, likely one of those two forms, okay, but it could be any of those three. All right, so see if you can calculate the arc lengths for these bottom two problems based on the information they provide and the formula from this set of three that you'll use for the calculating arc length. Right. If you're looking at this first problem, they want the arc length determined by central angle of 100 degrees. So here's the arc length from P to S that we're looking to measure or to calculate. And so when we look at that, we're looking at m over 360 times either d pi, 2 pi r, or c. Since they gave us a radius, we'll use 2 pi r. So we choose the formula that involves the information provided. Our arc measure coincides with the central angle, so 100 over 360 times 2 pi. Our radius was given as 17. So in my recommendation is just enter the calculation. It's the easiest way to do it. It shows your work, okay? And it does the calculation for you anyway. It'll show the calculated amount off to the side. But if you wanted to find what that calculation was, you can confirm it here, and you would get 29.67 for that measure. Okay, the last problem is asking for a similar thing. You're finding the arc length from P to Q with a central angle of 39 degrees. This time they gave you a diameter. So when you look at your formula, it's some portion of a circle circumference, m over 360, times d pi. So this time, since they gave you the diameter, we'll use the version of circumference, the formula for circumference d pi, and then just plug in what we have. So we have 39 degrees over 360 times our d value of 24 times pi. And so we just calculate that. And when we do, we get 8.17 approximately. And either of those is okay. Again, I recommend just entering your calculation. That would be the sort of ideal way to approach that. All right. 11.1, in addition to this, it repeats a concept that we've already talked about because I wanted to introduce it to you earlier. And that was the idea of how to convert between degrees and radians on a circle. So if you recall, 1 radian is the angle measure that cuts off an arc length equal to the radius of the circle. Okay, so when you find this arc length right here is the same as 1 radius, that represents 1 radian. And so that's what a radian is. And the conversion between radians and degrees, if you're starting from degrees, so you have x degrees, you would multiply by a full rotation around a circle is 360 degrees, and it's 2 pi radians. And so that is your conversion, which if we want degrees to cancel, we'll put degrees in the denominator, so the symbols cancel. And again, if 360 is equivalent to 2 pi, that means that 180 is equivalent to 1 pi. And so this right here is your conversion. You multiply by pi radians over 180 degrees. And if you're starting with radians, the conversion would need to cancel radians, so the pi radians would be in the denominator and 180 degrees in the numerator. And so this would be your conversion from radians back to degrees. And so see if you can calculate those here on the right. Like I said, we've already done these problems before, so hopefully this doesn't seem new to you. For the problems on the top half of this slide, I can't remember if it will accept calculations or the non-simplified forms of the answer. So I'll show you how to simplify it in case the problem requires that. Okay, but here, if you just start with the measure that's given, and then you use the correct conversion. So we're starting in degrees. So for degrees, we need the degrees to cancel. So the 180 degrees is going to be in the denominator. Pi radians is going to be in the numerator. So this right here would be your calculation. Now, if you are being asked to put this in form of a fraction like it says here, if it doesn't accept 210 pi over 180, you might need to reduce your fractions. If you do that, just use Desmos. If you type just the fraction part, leave off the pi, because pi is irrational. It can't be converted into a fraction form. But if you just take the numerical fraction part and you hit this fraction button, it'll reduce that down for you. And so you get 7/6. So 7 pi over 6, or 7/6 pi. And this would be your converted form. Okay, the next 45 degrees, if you take your angle 45 times, since degrees is the numerator, we need it to cancel with degrees. So 180 degrees in the denominator, pi in the numerator. And if you just took the ratio of those angles, 45 and 180, and then you could see here, the fraction bar though, fraction key gives you 1/4 pi or pi over 4. Either of those would work as your fraction form. Right, when you're converting from radians to degrees, here you'll put radians in the denominator. So if you were to take your, again, initial measurement and you convert, the radians needs to be in the denominator. So pi radians is equivalent to 180 degrees. And so there is your conversion. Once again, you can enter that completely. If you see this, the pi's cancel, and if you are looking to just type it in, 49 over 360 times 180 will give you your answer in this particular case of 245. And in the next, if we take our given angle measure in radians and we convert, radians need to cancel, so pi radians in the denominator, which leaves 180 degrees to be in the numerator. Your pi cancels, and once again you're left with just the fraction form, 17 over 36 times 180, and that leaves you with 85 for your angle measure. All right, so 11.1 is going to cover those concepts. 11.2 is going to extend to finding the area of a circle, which you should be familiar with. The area of a circle is pi r squared. Again, it's a pretty common formula you've probably been working with for a while. Okay, so I want you just, the problems on this page, this slide right here, are the basic problems, the ones that are just straightforward. So I want you just to take a moment here, make sure you can answer these, but these are the questions that I would have expected even before I showed this formula that you could have answered correctly. All right, so starting with the one on the bottom left here, if you're not specifically told this is the radius, okay, but you're given a diagram, you simply need to count or find your radius. Well, I see that it goes from -8 to +8. That means the center is right in the middle of that, at 0.00, the origin, and that tells you that the radius is going to be that distance to either of those points along the circle. It's a distance of 8, and so if you take pi times r squared, that's all you would have to do. You can enter it like that. If you entered the calculated version of it, that would be acceptable as well. 201 point to the nearest hundredth is 2 decimal places, so 0.06. But again, I would just type the calculation. It shows your work. It's easier to enter, and it will still display the calculation on the right side, and it will be exact. It'll extend the decimals out to as many places that it contains or that it can display. Okay, the other two problems are ones where they just give you the information. So 18 right here, you see that this is a diameter. So the diameter can help you find the circumference, d pi. So you get your circumference is just 18 pi, leave it as that. And then the area, if the diameter is 18, the diameter is equal to twice the radius, which means dividing the diameter by 2, 18 halves, which is 9, gives you your radius. And once you have the radius, the area is pi times the radius squared. So once again, you can leave it as that as that calculation. But if you type pi times 9 squared, you get 254.47. And if you type 18 pi, you would get 56.55. if you wanted the decimal equivalents. Once again, I encourage you to just use the calculation. The last problem, they specifically tell you that, in this case, they give you the area. So if you know the area formula is pi r squared and the area is given as 64 pi, you can substitute that in and solve. We want to isolate our r value, so divide by pi, and then extract your root. Normally when you extract the root, you have to consider both the positive and negative root, but radius has a built-in restriction because a radius can't be 0 or negative. It has to be a positive number. So we can disregard the negative root 64, and we're left with just the radius of 8. And if the radius is 8, the diameter is twice that, so 16. And these are just quick mental calculations. You don't need to do any calculating on those. Okay, so this is what I would, again, consider like very straightforward. You shouldn't really have any issues with these. All right, I'm going to slightly change the order of the slides. I'm going to jump to this slide on the area of a sector, and then we'll come back in just a bit. Okay, but when we're dealing with the area of a sector is just a portion of a circle's area. Just like an arc length is a portion of the circle's circumference. And so you're going to take the same calculation. That portion is representing m over 360, and then the area is given by pi r squared. And so it's just m over 360 times pi r squared is going to give you that calculation. Again, m is the arc measure, r is the radius. Okay, and so for both of these here, just really quickly, see if you can find their areas. And I encourage you just to use the formula. There's no reason, again, it'll calculate it and show you the decimal equivalent on the outside. But m over 360 times pi r squared, where your m value is 130. The radius is given as 4. And so that's as simple as it gets. You just type it exactly in as it appears. And you can do some of the individual calculations as well if you wanted to. 4 squared, I assume you guys are familiar and it's easy to work with. Or you can just leave them in that calculated form as well. Okay, next one is the same idea here. Just make sure that you're looking for the region that they are asking you, not the other region. So here we want the region that's cut off by 74, so it's the same thing, m over 360 times pi, the radius is 10 squared. We have our answer. You don't need to type anything else. And if you calculate you would get your solution to be 64.58 approximately. All right, so these are the area formulas that you need to be familiar with. So I'm going to add a few things that weren't on these slides. Okay, so the first thing I want to start talking about is we saw this relationship earlier. All circles are similar to each other. Okay, so what that means is just like with other similar figures, when it comes to ratio of parts versus the ratio of areas, okay, we have the same relationships that we've talked about with those other similar figures. Okay, if we have ratio of parts of m to n, then that means that the ratio of the areas of those similar figures are going to be that same ratio for every dimension being measured. Well, area measures in 2 dimensions, and so this is the relationships that we're looking at. Okay? And so what that would mean is, if I were to give you these 2 concentric circles, and I said that this was at the point 0, 5, and 7, if I wanted you to find what is the ratio of areas of the small circle to the large circle. Okay, so if I want to take that inner circle versus the larger circle, the outer circle, what would be the ratio of their areas? Well, the first thing I would do is determine the ratio of their parts. So I have a radius of 5 for the inner circle and a radius of 7 for the outer circle. And from that, I could then calculate the ratio of their areas, right? I take 5 to 7, and I square that, and that gives me 25 to 49. So this would be my answer. Now, be careful. The question may ask you to write your answer in this ratio form, 25 to 49 using a colon. It may ask you to write it as a fraction. It may, again, if it's a conversion factor, going from small to large would be 49 over 25. Going from large to small would be 25 over 49 if you're writing it in fraction form. And so once you get this information, what you do with it might vary slightly. All right. Once again, the next concept that I'm going to talk about, or the next 2 I'm going to kind of model here. I don't have slides for them. I apologize. But you can either take a picture of what I write, or you can copy it down. All right, so what if I ask you to do this? Find the shaded area of this figure, and all you're told is that this figure right here, and you are told also that it's a isosceles right triangle, has a leg of 13. Can you find what the total shaded area would be for this figure? And so these next couple slides, or the next couple examples of questions, are going to be ones that require a little more thinking and planning, and using some material from previous sections. So here's the basic strategy. You're either going to build up the different parts into shapes that you have formulas for, or you're going to break it down or deconstruct it into those shapes. And so for this particular one, we're going to build it up, because the area of this whole shaded region is this semicircle. Semicircle is a sector, right? It's half of a circle. So the m over 360 would be 180 over 360, which we can reduce to just 1/2 of pi. Oops, I'm going to do a visual first. So it's this semicircle, and then to that semicircle, we're adding this right triangle. So this is what we're forming for our total shaded area. So if we turn these into formulas, 1/2 of pi r squared, and then for the triangle, our triangle area formula is 1/2 base times height. And so what we need to do is find the different pieces of information. So here's the radius. We don't know that yet. For our right triangle, since the right triangle's legs are the base and the height, so we can use 13 for the base. And since it's an isosceles right triangle, these are equal. We also know 13 is the height as well. So the only piece of information that we're missing right here is this radius. Okay, and so for us to find the radius, we can use the following. If we took this right triangle, the isosceles right triangle of 13, 13, what do we know the hypotenuse would be? So 45, 45, 90, so we have x, x, x root 2. So that hypotenuse is 13 root 2, and the radius, the hypotenuse is a diameter, so the radius is going to be 1/2 of this, so 13 root 2 over 2. And there is our answer. You can enter your answer just in that form. if we're taking this whole thing, since I am going to square it, I take 13 root 2 all over 2, and I'm squaring that whole thing. So here's my calculation for that, plus 1/2 times 13 squared, or 13 times 13. And what I get for my estimate is 217.23. Area, remember, is a square unit. It's units squared. I most likely won't ask you to label the units, but just be aware that just like any areas, it's measuring a two-dimensional space, so it's square units for that. All right, I want you to try this same problem right here, except I want you to solve the other version of this. And the other version is if I gave you the diameter. Okay, so do the same thing. See if you can find the shaded region. But this time, instead of me giving you the leg of one of those, the leg of the right triangle, I'm going to give you the hypotenuse, or the diameter of the circle. And can you find what that shaded region would be? And so we have the same sort of visual calculation for the area, right? The total shaded area is the semicircle plus the right triangle. So it's 1/2 pi r squared plus the area formula for the triangle, 1/2 base times height. And so we just start plugging in what we have. Well, in this semicircle, if the diameter is 28, that means the radius is half of that, or 14. So we can plug that in. And now we don't have the base or the height here, but we do know the base and the height. These are the same measurements. Okay, and the easiest way, in my opinion, to find these is if you, instead of taking this diameter of 28 and trying to find what each of the legs is, which you still can do, and the pattern is actually like similar to what we're doing here. But if you just drew this in, drawing this radius makes these two sides equal, which gives you an isosceles right triangle once again here. So that means that each of these legs is 14 and the hypotenuse is 14 root 2. It fits this pattern as well. And that's just a nice easy way to find that the leg is 14 root 2, which means the other leg would also have to be 14 root 2. So if I'm entering if I'm typing this in, I would just put my formula here. And if you're calculating that formula, you can do so. And you get 503.88. It's once again square units if you're measuring those. All right, so this would be an example of constructing it up or building it up from the individual parts. Okay, the other type that you're going to see here, where it's more along the line of breaking it down, is going to look like this. And see if you can find this shaded region, please. And you can expect to see this angle right here will either be 30, 60, or 45 degrees. It's going to be one of those patterns, 30, 60, 90, or 45, 45, 90 triangle. We already looked in the previous couple problems with the 45, 45, 90. But if we have a 30, 60, 90, our pattern is x, 2x, and x root 3. And so be, again, aware of that. And this one you're deconstructing. So to find the shaded area, you're taking that right triangle and you're subtracting a sector from it. So the area formula for a triangle is 1/2 base times height. The area formula for a sector is m over 360 times pi r squared, some portion of a circle's area. And so if you look at this 30, 60, 90, that if that's 60 degrees, that means the side opposite 30 degrees is 6, making this leg 6 root 3, and this whole measure here would be double 6 or 12. So we have a height of, or a base of 6, corresponding height of 6 root 3, minus our degree measurement. M value is 60 degrees over 360 times pi. The radius was given as 6. And so once again, easiest thing to do is just type in the equation that you would use. If you're looking to calculate, or if you type that equation in, it will give you your calculated value. And just to confirm it, I get 12.33 approximately. And once again, it is square units since it is an area. All right, so again, these aren't the only examples. There may be versions where this central angle is 30 degrees, versions where it's 45 degrees, and so you'll randomly get one of those. All right, the last thing, I do want to go back to this slide here and talk about this concept called population density. A population density is just really identifying how many people there are within a given area. And so the calculation is just what is the population, and then divide that by the area of the land. And for this, as you would probably guess, since we're in a chapter dealing with circles, if you want to find what's the population density when you're looking at 42,000 people that are living in an area that has a 66-mile radius, well, the fact that you're using radius here means you're dealing with what shape? A circle. And so you're just plugging that in. So again, easiest thing to do is just type in your calculation. And if you do the calculation, you would get 371. It does ask you to round to the nearest whole number since you can't have fractions of people. And so on this one, now, it just wants you to round. So this one would round to 371. Okay, so again, you'll just cut it off using normal rounding rules.